Okay, so terminal velocity. When somebody is falling from the sky, they're going to have two forces acting on them. One is the weight of the person, and that's not going to change as they go down. But the other is drag. Drag is the air resistance pushing up. And the faster they go, the stronger air resistance is going to be. So here is, when you first jump out of a plane, there's weight, but there's no drag. But after you've been falling for a little while, you start to have the force of drag. I'll just call it drag instead of F drag, pushing up on you. And eventually, you get going so fast that drag pushes up with the same force the weight is pulling down. And when that happens, your net force is 0 and your acceleration is 0, so you no longer change speed. You stay at that velocity forever. So in this case, the net force, I'll just write as down, and your acceleration is still down because you've got more force pulling you down than up. So this is what it would look like before reaching terminal velocity, and this is what it looks like at terminal velocity. So when an object is falling at terminal velocity, the object's weight is the same as the force of drag. When an object is falling from the sky before reaching terminal velocity, the object's weight is stronger than the force of drag on the object. Okay, two kinds of, these are kind of like these, but you've got to set them up yourself and then solve for some missing component instead of a bunch of missing components. Got a 6 kilogram block or box. And it's sliding with the velocity of 5 meters per second. That really doesn't matter. I don't even have to draw that. Force of friction acting on the block is what we're trying to find. Sorry, need to get rid of that. The block's acceleration is 3 meters per second. That's important. And person pushing the block is pushing with a force of 30 newtons. That's important. We've got to find the force of friction, draw the box on the ground, and all the forces acting on the block. So here's let's do the weight. That's always easy. Weight equals mg. M is 6, g is 10, so that's going to be 60 newtons. And since the block's not going up or down, there must be a normal force, which is also 60 newtons going up. So those aren't really going to come into play in this, but they're there. They just cancel out. Somebody's pushing with 30 newtons, so that means that's positive. They're pushing to the right. So that's the 30 newton push. And then there's friction going the other way, and we've got to find that. So just like what I was saying earlier, we're going to need those two equations. And I'll do F equals ma, see where that leads. So the net force equals the mass of the block, 6 kilograms, times 3 meters per second squared, which is 18 newtons. So that's the net force. The other way to do net force is to add up all the forces. So I'm going to do that now. The net force equals this plus this plus this plus this. So this and this, they cancel, leaving them out. This is positive, this is negative. So I'm going to write this as 30 newtons minus friction. All right, so this is the net force using F equals ma. This is the net force adding up all the forces. So this is equal to that. So I can say 30 newtons minus the force of friction equals 18 newtons. And now I just need to solve this. So if 30 newtons minus friction equals 18, what do I need to subtract from 30 to get 18? And the answer is 12. You could also your math teacher would say, add this to both sides, then subtract that from both sides. And when you do that, you're going to get 12. Force of friction equals 12 newtons. One more in this section. This is the easier one. Kind of should have put this one before number 9. It's easier again because there are fewer variables. This is somebody moving up and down. So we've got somebody with this mass standing on a bathroom scale on an elevator. There's the scale reading. The scale reading is always the normal force. It's always the force of the scale pushing up. And we're looking for acceleration. So draw everything, show all the forces. Here we go. I'm going to draw this student looking square, 80 kilograms. Tiny little head, standing on the scale. There. So the forces here are the weight of the student and the normal force of the scale. So the normal force is just the scale reading, 560 newtons. The weight is mg, mass times gravity, so or mass times g, which is 10. So 80 times 10 is 800. And that's all I can do at this point. So remember the two things I'm going to do. I'm going to try to use this equation, and then I'm going to add up all the forces. And those are two different ways to get the net force. By doing those two things, I'll be able to figure out what the acceleration is. So sum of forces. Now, last time I started with this one, I can't do this time because I'm looking for the acceleration. I don't have that yet. I do have the mass, so I've got to wait on that one. This one I can do. The net force here is these two forces added together. This is positive, this is negative, so it's going to be 560 newtons minus 800 newtons, and that is negative 240 newtons. So that's the net force. Now I can use this equation. So I want to find acceleration though. So I know the net force is negative 240. I know the mass is 80. I need to find acceleration. Let me do this over here. You can either do the algebra the proper algebraic way that like math teachers do, or you can just say net force goes in the top, M and A go down there. If I'm looking for acceleration, it's going to be F over M. So A equals net force divided by mass. And the net force here is negative 240. The mass is 80. And when you punch that into your calculator, you will get 3 meters per second squared. Except it's not 3, it's negative 3. So there we go.